Before we do calculus with polar equations, it's important to just review the basics so that we know what to graph and just how points work. So basically at this point you've probably noticed that there are two different systems for plotting points in two-dimensional space. There's the rectangular coordinate system, or the Cartesian, which is what we're probably mostly used to because we use it more often. And you specify an x and a y coordinate and that will identify the point. But then there's also polar coordinates, which you hopefully learned about in a pre-calculus course, if not earlier. And here you specify a distance you walk out from the origin, which is called the pole, and an angle you rotate, where the positive x-axis or the polar axis is always where you start. So so those are just two systems of plotting points. They allow us to make graphs of very different types of pictures depending on the system you use. We can convert back and forth from one to the other. So what we'll do now is we'll get some review on plotting points, what basic graphs look like, because ultimately we're going to want to do calculus by finding derivatives and getting areas and all that stuff. By the way, this is not meant to imply that these 2 points are the same point in different forms. In fact, this first point in rectangular form would have coordinates in rectangular form. In polar form. That's 3, this would be 3 root 2. And since it's a 45, 45, 90, you could name that point, 3 root 2, 45 degrees. And likewise, this point here, if you want to write it in rectangular form, you might write it as 3 over root 2, 3 over root 2. In any case, let's get some practice with these two systems. Alright, so recall that when you want to plot a point in polar, you can either, again, we're always facing the positive x-axis, or the polar axis as it's called. So this says to essentially walk out a distance 3 from the pole and rotate pi over 4. So you can do that in either order. You can rotate and walk out, or walk out and rotate. Either way, it'll get you to this point right here. So that is the point 3 pi over 4. A negative angle would just mean you're rotating downward. So to rotate negative pi over 2 means you'd be facing down and you'd walk out 4. That would put you there. A negative radius, or a negative r value, means that you're going to walk 180 degrees in the opposite direction of where you would walk if that was positive. So if you rotate pi, you're facing sort of the negative x-axis is what we call it. And but rather than taking 2 steps out, you'll take 2 steps backwards from facing that direction, which would put you here. By the way, there is a flaw I should point out in the in what I've done here. Really a polar grid should not have these negative values at all. So I've kind of imposed the Cartesian coordinate system on a polar graph, but I think it's okay just to kind of get us somewhat oriented. But again, it really shouldn't be there. Here it says simple graphs in polar form. So to graph r equals 2, well, again, in polar form you're specifying an r value and an angle. And what this is saying is no matter what your angle is, you're going to walk out 2. So if you rotate 0 radians, you're going to walk out 2. If you rotate pi over 4 radians, you're going to walk out 2. Pi radians, pi over 2 radians, you're going to walk out 2. So that clearly specifies a circle. I guess in my case, a poorly drawn one. On the other hand, if theta is fixed and your r value can vary, then since theta is fixed, no matter what r value you put in, you're going to be facing pi over 3 radians, that direction. But pi over 3 is 60 degrees, so that would be this line here. So again, no matter what your r value is, you're going to be facing that direction. So, 2 pi over 3, 4 pi over 3, those are all points on this line. But of course, you could walk out negative. You could have negative r values, and that would bring you in the opposite direction. So that specifies a line through the origin. And lastly, r equal to -2. Well, that's going to have the same exact graph as r equals 2. even though the theta values might be slightly different for the points. But in any case, every time, any angle you face, you're going to take 2 steps backwards and plot a point, which would result in a circle. So you want to know how to graph some basic common graphs written in polar form, and really that ultimately will be graphs of that are circles, rose petal graphs, and these limacons. So let's deal with this first one here. R equals 3 cosine of theta. If you're having a hard time recalling what that looks like, it's always useful just to plug in some convenient theta values and to evaluate. So I might just plug in 0. Pi over 2 is convenient. I'm going to leave it here in the middle in case we need to do something more specific. Pi over 2, pi. So when you plug in 0, you get 3. Pi over 2, you get 0. And you plug in pi, you get negative 3. And so if you just plotted those points, 0, 3 would be here. Pi over 2 and 0 would bring you here. And then pi negative 3 actually replots this point here, interestingly. So that doesn't give us a lot of information. So you have a couple options. You can convert this to rectangular form if you remember that. You could plug in a few more values, which is why I left these spaces. So when you plug in pi over 4, you get 3 over root 2. Right? Root 2 is like a little less than 1.5, so this is, something that's a little bigger than 2. And when you plug in 3 pi over 4, you get negative 3 over root 2. Okay, so that should give you some sense. If you rotate pi over 4, you're going to walk out a distance that's a little more than 2. And if you rotate 3 pi over 4, that faces you, you're in the second quadrant, but you're going to walk backwards 3 over root 2, a little more than 2. So if you haven't figured it out by now, this is gonna graph a circle. So I'm relying a little bit on your prior experience with graphs like this, but a graphing calculator or something like that could actually help you to kind of get better at being familiar and recognizing these graphs ahead of time. R equals 4 sine of 2 theta is in a special form, and that, if you remember, is going to sketch a rose petal graph. Now, one way you can remember how to do that, how to sketch rose petal graphs, is to make, what I like to do is I like to sketch a quick graph of this in its rectangular form, where r is the y-axis and theta is the x-axis. So what do we know about this function? It's got a period of 2 pi over 2, which is pi, and if you just cut that into fourths, that will give you, it'll help you get the location of your first petals. So it says an amplitude of 4. So this graph behaves like this. And what this tells us is that the maximum distance we're going to walk out from the pole happens at 45 degrees, and we'll be walking out 4 at that instant. And that will correspond to a rose petal. If you're unsure about that, let's just kind of plot the, if you just made the table, you might have been able to reason that way. I'm not happy with that pi. But these values, if you plug them in, give you 0, 4, 0, negative 4, and 0. That should be enough for you to figure out the rose petal tips. So there's one there. There's going to be one when you're at 3 pi over 4, right? When you're at 3 pi over 4, you're going to walk out negative 4. All right, now that those are 2 tips. We know there's going to be 4. Since that's even, that means there's going to be 2 times 2. There's going to be 4 petal tips, and they're all going to be evenly spaced. They're all going to be evenly spaced, so they're all going to be spaced 360 divided by 4, which is 90 degrees apart. So far so good. It looks like these 2 petals are 90 degrees apart, so that must mean the other ones are here and here. It's important to remember that the way this graph is traced is not in the order that we sketch it, right? I mean, it actually looks like it traces the first half of the petal in the first quadrant, and then the first half of the entire petal in the quadrant 4. So the petal that gets sketched completely first looks like is the one in quadrant 4. So anyway, that tends to matter when you're making decisions, when you're doing integrals, in terms of what theta values to use. But we'll cross that bridge when that comes. This guy here is going to be a limacon, and again, I think I just recommend plugging in convenient values like 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then your R values corresponding to those will give you these. And so when you're rotating 0, you walk out 0, so we've got a point at the pole. Rotate pi over 2, you walk out 3. Rotate pi, you walk out 6, so I'm a little bit off the grid here. And rotate 3 pi over 2, you walk out 3. And then you're back to 0. So this ends up tracing this limacon. So those are 3 basic graphs. Probably, at least if you're in my calc class, those are really the ones we're going to focus on. We'll find areas inside them. We'll find derivatives, appropriate derivatives, etc. Hopefully this was a good overview of polar equations, and I'll see you in the next video. Sometimes it's nice to convert between rectangular and polar forms, in particular if you really want to know what you're looking at, and or if you just want to do calculus on a different form, maybe that appeals to you. So the relationships we'll need will be all within this triangle I'm about to draw. So this point right here, depending on the system we're in, I could call that r theta if we're in polar, but if I'm in rectangular form, I'd call it x comma y, so it has those 2 names at least. And again, if you're in the polar system, you're emphasizing the angle and the r value, whereas if you're in the rectangular system, you're emphasizing the horizontal and vertical distances you need to walk out to get there. So there are a few natural relationships we see. One is the Pythagorean theorem, so there's an identity we can use. Another one using our trigonometry is that the sine of an angle in this diagram is y over r, which means that y is r sine theta. And similarly, cosine of theta is x over r, which means that x equals r cosine theta. And these guys, and I guess, might as well throw in tangent. The tangent of the angle, at least in quadrant 1, will be y over x. But in any case, if we needed to convert this equation here, for instance, to rectangular form and identify the graph, what we might do is try to get some of these identities into play so that we can replace them. So one thing you could do if you wanted, for instance, to get an r squared in here and an r cosine theta is multiply both sides by r. You could square both sides and you would get an r squared on the left, so you could replace it with x squared by plus y squared, but then you'd have a cosine squared and a 64 on the right hand side, and there's no real identities. We haven't introduced an r value next to the cosine, so it doesn't really help in that sense. Multiplying gives us r squared equal to 8, and I want to sneak that r in between the 8 and the c in the cosine. So now that tells me I can replace this with x squared plus y squared, and I can replace this with x. Okay, so we've now successfully converted this to rectangular form. What we haven't done is, put it in a form that's easily recognizable to somebody who knows anything about equations in rectangular form. Although I guess if you know a lot about them, you'd recognize it immediately, like a math teacher's. We all know what this is exactly. But in any case, let's just complete the square, which is what I'm really getting at here. I'm going to minus 8x from both sides to set it equal to 0. And then to complete the square, I'm going to take half of the negative 8, which is negative 4, square it to put a 16 here, and then to balance, I'm going to add it here. That allows me to call this x minus 4 squared plus y squared equal to 16. And now we see that we're just looking at a circle with radius 4 centered at 4, 0. Alright, so again, just a quick review of how you can convert between the two systems.